Vanakkam. Welcome to this course on classics in neuroscience. In this series of videos, we have been looking at classic Nobel Prize winning works. Last week we saw the work of Santiago Ramon y Cajal and Robert Barani. This week we will see the works of Charles Sherrington, Edgar Adrian and Hodgkin and Huxley. In this series of videos, we will look at the classic Nobel Prize winning contributions of Charles Sherrington. So, who is Charles Sherrington? Charles Sherrington is the 1932 Nobel Prize winner in physiology or medicine for his discovery concerning functions of neurons. He pioneered the notion and the concept of synapses and reflexes and reflex integration, reflex arc, reciprocal inhibition and several topics. He also authored the famous text on the integrative action of the nervous system, which is considered a classic in the field of neurophysiology. In today's class, we will look at the personal background and timeline of Charles Sherrington. In this class, we will look at who is Charles Sherrington and his personal background and timeline, and we will also look at his major contributions to the broad field of neuroscience that led to the award of the Nobel Prize in 1932, and we will introduce some of the novel experimental approaches used by Sherrington. Charles Sherrington was born in 1857 in London in UK. He lived till about 95 years and passed away in 1952. He was a British neurophysiologist. He studied at Gonville and Caius College in Cambridge, and he had his medical training in St. Thomas Hospital in London. His research focus was primarily in neurology, physiology and experimental medicine. Early on, he worked in bacteriology, in cholera and diphtheria in Spain and in Italy. He was mentored by Langley, J.N. Langley, who essentially pioneered the autonomic nervous system study, and with his advisor, with his mentor J.N. Langley, he had, as a student, he had a couple of papers very early on. That was, I suppose, in the 1880s. And he also trained with Michael Foster, who taught him advanced physiology, which inspired him to continue on to do his extraordinarily advanced and pioneering work in neurophysiology. He was greatly influenced by Santiago Ramon y Cajal and his groundbreaking contributions that led to the first disposition of the neuron doctrine, suggesting that neurons are indeed individual cells and that neurons do not form part of a wide net or a reticulum. So, Sherrington's work supported Cajal's neuron doctrine in the sense that Sherrington actually suggested that communication between neurons happen at a specialized nexus between neurons, and this nexus he called as a synapse, and communication within a neuron is faster than communication between neurons. Essentially, there is a delay when there are two neurons involved, suggesting that there is a gap between two neurons. We will discuss this principle and this concept in good detail later, but this essentially nailed the coffin in the reticular theory, essentially providing a grand support to the neuron doctrine that neurons are indeed separate cells and communication between neurons is different from communication that happens within a neuron. Of course, in those days when he formulated this theory, it was not clear how communication between neurons was happening. That came only much later, but it still laid the groundwork for this theory. Apart from his research and science pursuits, Sherrington was also a fierce competitor in rugby and rowing, despite being just 5 feet and 6 inches tall. What are his major contributions to the broad field of neuroscience? First and foremost, he essentially defined and described the notion of a reflex arc and the concept of reciprocal inhibition. He discovered that there was reciprocal innervation that showed that when a muscle contracts, the antagonist muscle, that is the opposing muscle, which is called as the antagonist muscle relaxes. So, command from a motor neuron to contract a muscle also commands the antagonist muscle to relax. Of course, it is a lot more nuanced than this. We now know that there is a sense of co-activation or co-contraction that can be changed depending on the task situation and the condition. This is something that we now know, but still that is not a disproval of Sherrington's original idea that if when a muscle contracts, the antagonist muscle relaxes. This is critical for smooth coordinated movements. Otherwise, what will happen is that you are contracting both muscles simultaneously, thus increasing the apparent stiffness in the joint, which will lead to a very rigid joint. By the way, that is a problem that happens in older age, that is a common problem that is seen in people with neuromotor disorders. But here we are discussing about the healthy case. In the healthy case, whenever a muscle contracts, the opposite muscle relaxes. And Sherrington studied spinal reflexes using detailed experiments, and he described the probable pathways that led to the reflexes. In 1897, he practically coined the term synapse to describe how neurons communicate with each other. He showed that neurons do not form part of a continuous network, but rather communicate via gaps. That is why in the last class we said neurons are in touch with each other, but do not touch each other. Neurons are in touch with each other, but do not touch each other. This provided a major support for Cahal's neuron doctrine and disproving Golgi's reticular theory. Something that we did not mention in the camaraderie between Santiago Ramon y Cajal and Charles Sherrington is this little anecdote involving Charles Sherrington and Santiago Ramon y Cajal. I suppose in 1895 or 96, I am unable to recall exactly when, in one of those years, Sherrington invited Cajal to deliver a prestigious lecture at his institution. So, Cajal accepted this and went to give the talk. He was staying in Charles Sherrington's house for a couple of weeks. So, Cajal was given a room for himself. Weirdly, Cajal had this habit of locking his room and taking the key with him every day when he goes to the institute along with Sherrington. Mrs. Sherrington wanted to clean the room. Obviously, that being her own house, she had an alternate key. So, she opened the key one of these days after a few days, because Cahal was staying for a couple of weeks. Sometime in the middle, say 4 or 5 days later, Mrs. Sherrington opened the door of the temporary Cahal's room, and what she found completely stunned her. What she found was there was a lab inside the room. There was a microscope on the study table, and there were papers, manuscripts, samples, slides lying all around the room. It was so filthy or dirty from her point of view. It was essentially containing a whole bunch of academic stuff. There was exactly a 1 foot or less pathway that led from the bed to the door. Everywhere else there was papers, manuscripts, slides, samples, microscope and other such academic stuff. So, showing the dedication of this brilliant scientist that was Cahal. He was doing research no matter where he was. So, that obviously the rest of the story as to whether they actually checked in with Cahal or not is not known to me, but this is the story about Cahal and how Mrs. Sherrington was stunned by having a mini lab inside her own house without her own knowledge. And so, Cahal shared this camaraderie with Charles Sherrington, and Charles Sherrington's theory and the idea of synapse provided the grand support to Santiago Ramon Cajal's neuron doctrine, and essentially dethroned reticular theory in a very big way. We will continue to discuss this in later videos. It was Charles Sherrington's early ideas that perhaps first or among the first ones to discuss that neuronal connections can change over time, over experience. This was also something that Cahal discussed. So, you cannot completely credit Sherrington for this. So, Cahal also kind of pointed to this in saying that look, if the neuron remains static, then there is no chance of learning. Recall this, we saw this in the last week's lectures. So, there is a necessity for connections to change or strength of the connections to change, which essentially encodes learning. This was an idea that Cahal also posited. Sherrington also suggested this, that so one of the early proponents of the idea of neural plasticity, but today this is a huge field of research, the field of neuroplasticity, and suggesting that neural plasticity exists at multiple levels within the central nervous system. It happens not just within the brain, but it also happens even at the level of spinal cord. It happens at the level of reflexes. So, this idea of neural plasticity was although suggested by Cahal, Sherrington provided some experimental evidence to show that perhaps this is indeed true. To support this idea, Sherrington provided some experimental evidence. One of the equipments that Sherrington used in his experiment was the kymograph. Is a device that is used to record muscle contractions when the nerve is stimulated. So, essentially when you know and record the time stamp of the stimulation, how fast or slow is the response is something that you can measure from the response of the muscle. Look how this is working. So, there is a drum on which the pen is writing. So, it was quite tedious to read the outputs from this kymograph and correlate it with the timing of the stimulation itself. Those are the days in which scientific research was indeed quite hard to perform. In today's world, this is just child's play. We can record data with a $50 or 5,000 rupee chip or boards, hobby boards that are available, MyoWare, whatever. There are several hobby boards that are available, small microcontrollers available to record this, that directly input your data to a phone, for example. But I am talking about these experiments that were performed about 125 years ago. And Sherrington practically invented this method. So, novel method to record both the timestamp of the stimulation as well as the response, thus knowing how much gap is there between the stimulation and the response. The longer the gap is, the hypothesis is that the more number of neurons are involved in the communication loop, so essentially suggesting that for each delay there is a gap that happens between neurons. Of course, this is not a specified unit, but still it is a rough or crude estimate of how many neurons may be involved, how many synapses may be involved in between the stimulation and the response. And he also used induction coils to provide controlled shocks to stimulate the nerves and observe the responses. He practically invented this method. And to study the visual system, to study visual processing and the response of the nervous system to light, he used flicker lantern. And in collaboration with Eccles in 1930s, he also practically invented the torsion wire experiment, which allowed very precise measurement of the neuronal signal transmission. All these things are innovations, experimental innovations that Sherrington performed in his lab. Note that he was not an engineer, he was a medical professional by training, but he was this rigorous scientist who believed in measurement, in measuring things, in measuring quantities. So, he wanted to know the time difference between events, which is how he went on to make his major contributions, which are essentially relevant to reflexes and reciprocal inhibition. So, with this we come to the end of this video. In this video, we looked at who was Charles Sherrington and his personal background and timeline. What were the major contributions that Sherrington made to neuroscience that led to the award of the 1932 Nobel Prize in Physiology and Medicine, and the novel experimental approaches that were used by Sherrington. Thank you very much for your attention.